Now we'll have a very brief coverage of temperature measurement. Temperature measurements for relative humidity occur in air, and the associated temperature measurements will also occur in air. Accurate air-based temperature monitoring has some particular challenges. Air is a very poor thermal conductor, and it does not hold its temperature particularly well. So temperature gradients are very typical when we're trying to make an accurate temperature measurement in air. For industrial temperature measurements, there are 3 temperature sensors that cover the vast majority of temperature measurements today. And they are thermocouples, which are great for wide range from cryogenic to very hot. RTDs or resistance temperature devices, which can also cover a very wide range very accurately. And thermistors, which although have a fairly narrow range, they're quite accurate over that range. Typically, RH measurement is performed over a relatively limited temperature range, so RTDs and thermistors are particularly well suited for that application. Thermocouples have a very wide operating range, but their accuracy typically suffers, particularly over the range of humidity measurement. Now we'll talk about actual measurement of relative humidity. Here is a slide I wish I had seen many years before. This is the measurement capability of a good primary or national standards lab. If we look at the measurement uncertainties, which is really like accuracy of things like frequency or mass or even temperature, the measurement uncertainty is extremely low, which means we can very accurately measure these parameters. However, if we look at relative humidity, we see that the best capability virtually in the world is 0.2%. Now, compared to these other parameters, this has very high measurement uncertainty, or a relative guess. Drift in a sensor or a measurement device is a random movement that's unwanted, that does not follow the true environment or parameter that's being measured. And so we can imagine it's not something that we want. All measurements have some level of drift, but few industrial measurements are more prone to drift than relative humidity. And one of the key reasons is that the internal structure of a relative humidity sensor is exposed directly to the environment. There is no hermetic sealing of the internal sensor elements like we can do in temperature, for example, because the sensor must be directly exposed to the environment, typically air, in order to measure it. And it's this air-breathing effect that exposes the sensor element to various contaminants and chemicals. And these, in turn, can cause and do cause drift. Initial measurement uncertainty, or accuracy, is, of course, very important to any measuring device. This is the accuracy that's obtained right after a calibration, or what I like to call fresh from the factory. While it's important, it's the as found or the recalibration accuracy or uncertainty that really you have to live with. One always has to ask, what would you have to do in your process or with your materials or system if you were to find that after recalibration, a sensor is considerably out of tolerance, that it's drifted? In some applications, that could have enormous implications because you really don't know when it drifted. Was it just the day before it got sent in for recalibration, or was it the day after it was initially calibrated? So it's very important to pay attention to the as-found measurement uncertainty. Within RH measuring devices, there are 3 common sensor types. The first are sensors that have some physical reaction to changes in relative humidity. These can be mechanical changes, electrical resistance, or electrical capacitance. The second type of humidity measuring device is called a psychrometer. And the third basic type is a chilled mirror hygrometer. The earliest documented hygrometer or humidity measuring device is Da Vinci's. And this consisted of a ball of wool. At low relative humidity, the ball of wool would not attract or absorb much water vapor inside it. so it would be quite light. As the relative humidity increased, the ball of wool would absorb more and more water vapor and would increase in mass. And this change in mass could be weighed. The weight of the ball of wool would correspond to the relative humidity. In the evolution of relative humidity measuring devices, the next step was hair, both human hair and horse hair. Hair will change its length in response to the relative humidity. Now, it does not have particularly high accuracy, nor is it particularly stable, but it can provide excellent chemical resistance. We can see here in the diagram that the hair is connected to a beam. And as the hair contracts or expands, this beam is deflected. And there's a pen on the end of the beam, which is writing to a rotating drum. So as humidity changes, the beam deflects, and that's recorded on a drum. Circular chart recorders are virtually identical, but instead of a drum, they just have a circular chart. But again, there is an arm or a beam that is deflecting as a function of relative humidity. Resistive sensors are also used to measure relative humidity. In this case, we have two isolated conductive electrodes. The sensor element is coated with a material that absorbs humidity and also changes the electrical resistance. These types of sensors are prone to saturation and contamination problems. These are typically not very accurate devices and are commonly used in white goods, such as the automatic turn-off cycle of a clothes dryer or to control a fan in a bathroom, for example. Psychrometers are another form of humidity measuring device. They work with two thermometers, one called a dry bulb, which appropriately is a dry thermometer, and the second thermometer is called the wet bulb. This thermometer has a cotton sock on it that is soaked with water. And by having airflow across the two thermometers, we'll see a temperature difference between the two thermometers. This temperature difference corresponds to the relative humidity. It reminds me of a story when I spent a summer in Tucson, Arizona. It was very hot, but very dry. And when kids would play in the swimming pool and get out, although it was 100 degrees, they'd feel cold and they'd jump back into the water. It seems strange that here it is 100 degrees and kids are chilly. And it's because the water would evaporate so quickly because the humidity level was so low that it would cause very fast and very acute cooling. Now, a psychrometer works the same way. When the humidity is low, the wet bulb will be quite a bit cooler than the dry bulb. This is called depression. When the humidity is higher, the temperature difference between the two is much, much less. And if one looks at the temperature of the two thermometers and consults a psychrometer chart or table, one can make a determination of the humidity based on the two temperatures. Now, shown here in the diagram is a sling psychrometer. One takes this and twirls it around your head to get the airflow. The problem is if the operator sweats at all, you're actually producing higher humidity. So not a very good ideal observer if you're actually generating humidity in order to make the measurement. Some psychrometers will actually use a fan to blow air consistently across them, and that yields a much more reproducible measurement. Again, psychrometers do have some very specialized applications, but they are not typically used for general humidity monitoring.